In this chapter, we're going to look at sampling distributions. And so what sampling distributions, the whole purpose of it is that typically we're taking a sample of a larger population. And essentially what we want to know is what is the distribution of various values based on those samples. So essentially what we can imagine that we're doing here is that um, we're focusing our attention now not on populations but on a sample, and we're just looking at we're focusing on how we describe that sample. So what we're going to start off with doing here in this chapter is we're going to start out with looking at the probability distribution within that sample. That would mean that, generally speaking, we're going to be looking at the mean, we're going to be looking at the standard deviation of those values, and then we're going to do it for the sample as well, and then look at what the consequences are when the sample size is large enough. So let's start out with an example just to make things a little bit clearer here. So let's say we've got 4 rowers that weigh 152, 156, 160, and 164 pounds. So we want to find all the possible random samples of 2 within that. So we have a set of 4, and essentially what we see here, and you could write it out yourself, but there are 16 possible different samples that could be drawn of a grouping of 2 from this set of 4 weights. Okay, so with those 16 different samples, right, so I can pick essentially what I could find here is that I could, as I pick 2 rowers, right, I could pick the same one twice, 152, then the mean would be 152. I could pick one and it could be that same 152 weighed person, and then I could pick a second that would be 156 pounds. Now what's the mean between those two? 154. So I just keep going on through all 16 of these. So if we take every possible sample from the population and calculate the mean, then those numbers in general would give us an idea of the population mean. So here's what we see here. We've got 4 values, 152, 156, 160, 164. So we've got 4 values. We have 16 samples. That's this, right? Picking 2 individuals. And if you look at this, you'll also see that we have seven different mean values. Right here. So if we just created a new table and we organized all those mean values, we would see that out of the 16, there was one that had a mean score of 152. That was the very first one. There were 2 that had a mean value of 154, 3 that had a mean value of 156, and so on and so forth. These add up to 1. All of them exist here. But now you should get a sense of the frequency distribution now within this. That the most popular or the most frequently occurring mean value is 158. And what that gives us an idea of doing then is probably more likely than not that the mean of the population of a whole is going to be closer to 158 than it is going to be to any other number. So let's find it. Let's prove that that's the case. So we've got a formula that we already had before. and that was, let's take each of the values and multiply them by their probability. So there's a 1 in 16 sample chance that we're going to get a score of 152, and we're going to add to that the 2 in 16th chance that I have of getting a 154, and so on and so forth. And if you do that for all the values, look at what you see. That the mean is 158. So the mean of the means is 158. Now, what that gives us an opportunity to then do, once we've calculated this mean, is that we then need to calculate the standard deviation. So let's do that. To do that, we're going to subtract the mean from the mean of the sample. So the mean of the sample, that very first one is 152, and then we're going to subtract the mean for the whole entire population, 158. We're going to square that and multiply by the probability. So that's what's following right here, right? The mean of the sample minus the mean of the population, squaring it, times the probability that it occurs. Add that all up, and we get a value of 10. And with that understanding of our variance, we then take the square root of 10. And I'm just going to confirm that that's the case here on my trusty calculator. Yep. And we get a value of 3.16. So now our variance is 10, and we took the square root of that to get the standard deviation of 3.16. So now we have a mean score, and we now have a standard deviation. The mean being 158, and the standard deviation being 3.16. Now, what's nice about this, so this example that we just did is not a, doesn't fulfill this condition, but what's nice is that there is a statistical phenomenon known as the central limit theorem. And this is the start of section 6.2 in the book. Essentially what it tells us is that when the sample sizes are larger than 30, then most of the time, not all the time, but most of the time, we'll have a mean and a standard deviation where the values are normally distributed. And the larger the sample, the more likely it is that we have that, that the mean that we find from the samples and the standard deviation, that's going to be closer to the population from what we have in our sample. So basically, bigger is better. And that's essentially what we see here. That's the lesson that we see here. And this is basically, I don't know why the book thinks that they have to tell it to you this way, but the book also wants to show you that, again, as the sample size gets larger, and you can kind of see that here, as the sample size is getting larger, that you see this more normal distribution emerging. I don't know why they feel that they need to show you more pictures of this, but it is in fact true. As you can see, as the sample size gets larger and larger, that it does become more normally distributed. Basically, these are bad shapes. Well, it's not that they're bad, but we can't do as much of them statistically with these as we can with the bottom, which are normal distribution. So, why should we care? Why should we care about the central limit theorem? essentially what it does is that if the sample size is large enough, we can then make meaningful statements, probability statements about the sample mean. Essentially, that there are two things basically going on at the same time. One is that we we have a continuous random variable, and that we know that within that population that there's a population mean and a population standard deviation. But the idea is that we might not always be able to realistically be able to measure everything in the population. So that's why then it's meaningful to have a sample size that's big enough so that we can actually talk about the population standard deviation and the population mean without actually having to look at the entire population. As long as our sample size is big enough, the central limit theorem suggests that we can make that shortcut. So let's look at an example here of how we would do that. So let's say we have a random sample size of 100. Ding, 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 right? That should say to us that central limit theorem likely applies. And here we're being told that the population, so in this case I do know the population, that the scores are 2.61 in the population, the mean score, and the standard deviation is 0.5. Now, what if I then take a sample of 100 from that entire population? And here I already know what the mean and standard deviation is. Essentially then, what is the probability that that mean score in that sample size is, we know that it would be 2.61 because our sample size is large enough, but what's the probability that it's going to be between 2.51 and 2.71? Essentially 0.1 above and 0.1 below the mean. 2 standard deviations away, essentially. I'll repeat that again just because I was saying quite a bit there. We are trying to find the probability that the sample mean, which we know should, because of the central limit theorem, should be about 2.61. And we know that because central limit theorem suggests that if the sample size is big enough, then the sample mean will be pretty darn close to the population mean. So now we're saying, what's the probability that I'm going to be within 2 standard deviations, or, well, actually no. So yeah, what are the chances that I'm going to be not 2 standard deviations? What are the chances that I'm going to be within a fifth of the standard deviation, right? Yeah, a fifth of a standard deviation away from, sorry, I misspoke there, because the standard deviation is 0.5. So that would mean yeah, sorry, I misspoke there. So we want to know what's from 2.51 to 2.71. So that would be 0.1 above or below when the standard deviation is 0.5. So a fifth of a standard deviation, because right, 1 over 5 is a fifth, 0.2. So what are the chances I'm going to be within a fifth of a standard deviation away from the mean? Well, again, sample mean, we already know what it is. It's the same as the population, 2.61. Standard deviation here is going to be my, of the sample, is going to be the standard deviation of the population divided by the square root of the sample size. 100. And we're going to see that there's a 5% chance. Not too surprising, because it is actually pretty close to the mean. So we just use this right here. So now we need to find the z scores for each of these values. So now what we're going to do is take each of our values, 2.51 and 2.71, and we're going to subtract the sample mean. In this case, 2.61 that we knew from the from the central limit theorem, and we're going to divide by the standard deviation that we found on the previous slide, 0.05. And we're going to see that we're looking for z-scores in the probabilistic range between -2 and 2. So, -2, right here, 0.0228. And we're looking for +2. That's 0.9772. And 0.9772 minus 0.0228. That difference is our 0.9544. So in this case, we see, at least from a range perspective, that 95% of the values would exist in that range. Now, what happens with when we're looking at that mean and standard deviation from our normally distributed population? What do we do? What do we do with that essentially? What do we, how do we understand it for the sample versus the population? So again, what we see here is that again, the larger the sample size, more normal distribution. And essentially then what we want to be able to do is you would use this kind of thing when you're taking like when you're doing quality control stuff and you want to look at a sample, that you're taking a sample of, let's say, items that are produced, and you want to be able to make generalizations to the population of all the items you're producing. That's more likely where you would see something like this. And so that's kind of the inspiration for this right here. So let's say we have a tire. That tire is designed to go 38,500 miles. At the standard deviation of the population is 2,500. And that then we're going to look at 5 different tires. Okay, so we're going to take, of the population, we're going to take 5, we're going to look at 5 tires. What are the chances that my sample mean is going to be less than 36,000 miles from those 5 that I'm looking at? Okay, so now we set it up. They're going to take out the thousands. That's what they did here to make our life easier. I'm not sure if that's really how much more complicated my life was like that, but whatever. So we know that the population and the sample, as it was said right here, is 38,500, standard deviation 2,500. What are the chances that it's going to be less than 36? So we want to now find everything less than 36. So essentially, what we want to do is take our standard deviation of 2,500 miles They mean hundreds of miles, not thousands of miles. I don't know why they say it like that. Because this would be 2,500 miles. Essentially, we take our population standard deviation of 2,500 divided by the square root of the sample size of 5. And we get 1.1. And we now know that we're looking for a z-score, which is going to be less than the 36 minus the mean value over the sample's standard deviation. So 36 minus 38.5 from the sample mean over the standard deviation of 1.11 means that we're looking for the probability of a z being less than negative 2.24. Negative 2.2 2.24. So that gives us our 0.0125 number. And it's going to tell us our probability of being less than that. Hence the 0.0125. That would be our probability of being less than 36. Now, what we'll find that we can do as well is that we can apply things to the population. So the proportion p hat, it's going to be it's going to be normally distributed when the sample size is large enough. So that would be basically mean as long as the sample size is large enough that, again, our mean of the proportion will be pretty darn close to the population mean, and that the standard deviation of the proportion will also be pretty darn close to the standard deviation of the population of a whole. So the question would be, unfortunately it's not as easy as the central limit theorem, how big is big enough? So what we need to do is we need to look at the sample size, and we need to look at the proportion, the distribution of the proportion size as well. Two conditions both need to be satisfied here. That n times p is greater than 5, and that our n times q is greater than or equal to 5, where that q is equal to 1 minus p. Let's actually look at a example here to make this a little bit more meaningful. So let's say that our sample size is 15, and that the mean of our proportion is 0.5. Well, 0.5 times 15 is 7.5. That's greater than 5. And n times q, that's going to be 15 as our n. And then remember the q is 1 minus p. So 1 minus p is 0.5. So that's also greater than 5. And what that allows us to do is it allows us to then say that the distribution of the proportion is going to be normally distributed. And we can see that right here. That most of our values here, as you can see here, are within 3 standard deviations. Most of our values are within 3 standard deviations away from the mean. Now, let's do a last example here that can kind of show an application of this. So let's look at a population of voters and look at them voting for a bond issue. And I'm going to take a proportion of those. I'm going to take 900 of those people and ask them if they favor the bond issue. And what I need to find out is this sample size big enough that it's going to be normally distributed? And then if it is, what's the probability that I'm going to be within 5 percentage points of the population proportion? So that's what we're trying to solve here. So let's make sure first, easy one, let's make sure we're big enough. We're going to do our n times p and then our n times q. So population proportion size 900 times 0.38. The 0.38 coming from the population proportion. And what we can see here is that that gives us at least a value greater than 5. And then we can take the sample size of 900, multiply it by 1 minus p, 1 minus p, and that gives us a value that's greater than 5. So what do we know here? We now know that it is going to be normally distributed. Now, to know what we need to do to be within 5 percentage points, then that would mean I'm looking for a score between 33% and 43%. Okay, right, because that's 0.05 difference of the 0.38. So now I need to find my z values, my z statistics for those. So I'm going to take the proportion, the value, 0.33, and I'm going to subtract the mean. Divide by the standard deviation. Take the number, 0.43, subtract the mean, divide by the standard deviation. Now, the question here would be, how the hell did they get that 0.01618? Well, remember, we can calculate it right here. So that would be 0.38 times 1 minus 0.38 divided by 900. And that should give us this value here. Not sure why they didn't write it out for us, but whatever. And if we solve that, we get scores of negative 3.09 and 3.09. Negative 3.09 is 0.0010. So that would be our left tail. .09 would be 0.9990. right here. That's our right tail. And so you see you have to subtract the 2 because now we're not trying to find the tails. We need to subtract the right tail from the left tail. And when we subtract those 2 values, we find that 99.8% of what we've got all going on is going to exist within 5 percentage points of that population mean. It's a pretty broad scale. That's going to cover most of our individuals. Okay. Again, in those lectures, I'm just trying to give you an idea of the general theory. Hopefully when I make my problem set videos, that'll give you a little bit of a better idea too of the application of things.